Greetings, math friends. I had seen over on the channel Mental Math that a problem of the form of this function had been posted over there, and it generated several comments and discussion in the comment section. One commenter, Amazing Calvin, asked a question about generalization. And we love those types of questions in mathematics. It gives us an opportunity to write a proof. So I've tried to tighten this up and formalize it a bit, and it's kind of stated in the form of the type of exercise that you would see in like Gaughan's analysis book. And now we're going to attempt to prove this, and I'm going to do two proofs. I'm going to do one that's a very formal and a real analysis epsilon delta style proof, and then we'll do a real quick proof by way of contradiction at the end. First of all, we need to tighten this down and make sure that we know exactly what we're talking about, because that really helps with mathematics. We don't like things to be ambiguous. So what we're going to do is we're going to state this in the form of a theorem and then prove that it holds. If f is a function such that f goes from the domain of the real numbers, remove a, to its range, where f of x is x squared minus a squared over x minus a, then 2a is not in R, which is our range. We'd like to prove that. This is a nice little relationship of the choice of a telling us that, one, that choice is not going to be in the domain, and two, twice that value will not be in its range. First of all, as with these types of things, we are going to let epsilon be an arbitrary real number greater than 0. And I'm going to draw a diagram with this. So I want to graph this function. We're going to have, it's going to look very linear. It's essentially aligned with a point discontinuity. This is going to be a. The y-intercept is also a. And then if we come up here to this point removed and look at the value on the y-axis, that's going to be the 2a. So this is essentially what our diagram looks like. When we choose this epsilon, we're saying that we have some real number is larger than 0, so it's a positive number, that we're going to add to 2a and subtract from 2a. So we just create this little interval that we're going to focus on right here. All right, I am fleshing out some details here that you may not normally see entirely fleshed out, but I think that's going to be good for seeing this come together. The next thing that I want to do, now that I know that there's a positive real number that creates this neighborhood here, there must exist another positive number that I can add to a and subtract from a down here on the x-axis to create a neighborhood around a. Now, this is a deleted neighborhood because a is not really a part of our domain. We, by tradition, call this the delta. It's also going to be larger than 0. It's a positive number. We're adding and subtracting to this. Now that we've presented these ideas, we're just going to do a little bit of algebra to demonstrate some very definitional ideas that we expect to see in real analysis. I'm going to start with the first idea, this epsilon neighborhood centered at 2a. This is, of course, on the y-axis, which means this is a part of the definition of the range. It's a part of where f of x lives. Since this is the smallest number in this interval, we know that it is smaller than some of the f of x's that exist. And that f of x, whatever it would be smaller than this, which is the largest number in this interval. So there's a bunch of f of x's in here. Now that we have this, I'm going to collapse it a little bit. I want to add a negative 2a across all three pieces of this compound inequality. That's going to leave me with the negative epsilon here is less than f of x minus 2a, which is less than positive epsilon. And then one thing that I'm going to do more is I'm going to collapse this again to make it an absolute value statement. Since this is trapped between these values, positive on one side, negative on the other, we can rewrite this statement as absolute value. And this says the same thing. So if this statement is true, and that's the way that we've established it here, we've just chosen this arbitrary real number and added and subtracted it. If this is true, this has to be true, and if this is true, this has to be true. So we have that the absolute value of the difference between these f of x's and the center of this neighborhood has to be less than epsilon. However, we know that epsilon is, again, larger than 0. Okay? So there's a limit idea in here. We're going to go through and do the same type of argument with our delta here, our delta neighborhood. We rewrite this as an inequality, but in the center, instead of being f of x, it's just going to be x because this is happening on the x-axis. So we can say that a minus delta must be less than x, which must be less than a plus delta. And then we add the negative a across here. So we have negative delta must be less than x minus a, which is less than delta. And then we collapse that one more time for the absolute value. So we have these two statements. We need one other thing that's an expectation here. I would need to make an extra statement about this inequality here. If x and a are equal to each other, this can go to 0, and we have that 0 is less than delta. And we can definitely make this statement because a is not in this neighborhood. It's a deleted neighborhood with the center missing. So a is definitely not here. So we can make that notation. X is never going to be equal to a. It's not in the domain. So this never goes to 0. It's absolute value, which means it's positive, so it has to be larger than 0. And since this is smaller than this, but larger than 0, we actually have that this value is trapped between 0 and delta. Again, this real number that we have existing. So I'm going to have to erase this to continue on with the argument, but we have two very important pieces of information that we need to hold on to. This statement and this statement. I'm going to talk a little bit about individual elements here. The domain can be written as sequential elements of x sub n, where x is just some element of the domain, and we can list them out as a sequence, the first term, the second term, the third term, and so on. So x sub n is an element of the domain. That would mean that f of x sub n would be an element of the range. We're going to say something else now. There exists another real number, capital N, and this capital N is just some number in the sequence, but it's a distinctive number in the sequence that we're going to call out and say something about. So there exists N such that for all n greater than big N, when delta is larger than 0, this implies that f of x sub n minus 2a is going to be less than epsilon. This implies that f of xn approaches to a. As x sub n approaches a. Since f of a does not exist, then f of x sub n never equals 2a. As I approach here, I never reach a. So as this interval focuses in on the center of that interval, this interval is focusing in on the center of this interval. I can never reach a here because it's a deleted neighborhood, which we stated earlier. And even though 2a is here on the y-axis, I can never get to it because I can never close this interval to reach the center of this interval. F of a is essentially 2a. This is the limit. I don't reach it. And that concludes our proof using an epsilon delta argument. Now that we've looked at a more rigorous approach to this, we are going to come back here and do a proof by contradiction. So right away, we're just going to declare, by way of contradiction, assume 2a is in R, which is the range of this function which we've already defined. Then we are going to let 2a equal the function. Since this is our value, we're replacing it with 2a, and that's going to be equal to this function here. And then now we're going to do some algebra. So I can use the difference of squares here to get x minus a times x plus a all on x minus a. These are going to cancel, leaving me that 2a has to be equal to x plus a. Solving this for x, I'll subtract a from both sides, and this gives me a is equal to x, and there's my contradiction, because x being a is a contradiction of the definition of the function, which says that a is not a part of the domain. Therefore, we must conclude that our assumption was wrong and 2a is in fact not in the range. So this is the contradiction. Hopefully that is good for most people to see these two different discussions. Tightening the definition of the function itself is really foundational with eliminating some of the conversation pieces that happen where we can say, well, if you assume this, you assume this, these are the conclusions, of course. If we define it more firmly to begin with, it takes away those if you assume, because we've already given the definition of what we exactly want to happen. I hope my epsilon delta argument was rigorous enough for most people and hopefully not too sloppy for those that are used to epsilon delta arguments. I hope you find some mathematics to share with others and enjoy. Cheerful Calculations.